Hi and welcome to this video today. In this video, we are going to use the framework that we have developed, namely the framework of vector spaces, to characterize the solution spaces of systems of linear equations. So this section is about solution spaces of SLEs. Basically, that is a summary of what we did and then application to solution spaces of systems of linear equations. We're going to revisit this whole idea later on when we've developed more terminology, more detailed characterizations. And we're basically going to rephrase that and add a few more details, but the main result is already here. So the purpose of this section is to summarize a first characterization of the solution spaces of a system of linear equations in terms of vector space language. Okay, we are now ready for this first characterization. Of solution spaces of SLEs using the language of vector spaces. And the main result here is the following. So here's the theorem. The solution space of a homogeneous system of linear equations with n variables is a linear subspace of R to the n. We already know the solution space, of course, is a subset of R to the n, and what this theorem adds is the characteristics of that subspace or that subset. It's not just any subset, but it needs to be a linear subspace. So the solution space for a homogeneous system of linear equations. Remember, homogeneous means the right-hand side is 0 with n variables is a linear subspace of R to the n. And because this is such an important and fundamental result in mathematics and in linear algebra in particular, I'd like to give you the proof of that result. And of course, I do hope that this also helps you to apply the notation and the languages of vector spaces in general a little better. So let's start with the homogeneous system of linear equations and let S be its solution space. So homogeneous means the right-hand side is 0, so the system will look like this here. So that is a homogeneous system of linear equations in tableau form. And let S be the solution space of this system of linear equations. We need to prove that S is a linear subspace of R to the n, and that basically means we have to go through these three subspace properties. So we show that S is a linear subspace of R to the n. We start with the first property that simply states the space should not be empty. And as you know, we usually do this by checking whether 0 is contained in that space. And that is, of course, the case here. 0 is obviously a solution. If we just put 0 for all the variables in that equation, then all the left-hand sides will become 0. So as the right-hand side is also 0, that means the equation is obviously satisfied, or all equations are satisfied. Okay, so the 0 vector, and remember that means setting all variables to 0. Is a solution to this system of linear equations. And in particular, that means the solution space is not the empty set. There is at least one solution. Now, the next two steps are a little harder to see. First, we need to prove that S is closed with respect to addition. That means we take two elements of S, or two solutions, and then we prove that the sum of any two solutions is again a solution. Okay, so the next point is closeness of S with respect to vector addition. Consider any two solutions of the system of linear equations. We call those x bar and y bar. Those are elements in S. And define, let's say, z bar is the sum of x bar and y bar. And we need to show that z bar is contained in S. In other words, it is a solution to the system of linear equations. So what do we know? For all equations, we have, let's say, m equations. For I and m, we have the equation a I1 x1 plus a I2 x2 and so on up to a in xn equals 0. What does that mean if we substitute z bar for x? Well, let's see. ai1 z bar 1 plus and so on up to ain z bar n. What is that? Well, z bar is x bar plus y bar. So we can use that first. So z bar 1 is x bar 1 plus y bar 1 and so on. Now we can rearrange that a little. Let's collect all the x terms and all the y terms together. If we do this, we get ai1 x1 bar plus the next will be ai2 x2 bar and so on up to ain xn bar. So that's the x terms. And then we have the y terms. It's ai1 y1 bar plus and so on up to ain yn bar. And now you remember that both x bar and y bar are solutions to the system of linear equations. So in particular, they will satisfy each and every single equation. So what that means is this equation here is satisfied by x bar, or more precisely the equation this equals 0. So this is 0 because x bar is in S. And the same is true for this side here. This is also 0 because y bar is in S. So what do we get here? Well, we get 0 plus 0. And this is, of course, 0. So what we have shown is Z bar really satisfies our system of linear equations. It satisfies every single equation. So it satisfies the whole system, and that means it is contained in S. So that's the proof of this second property, closeness with respect to vector addition. And what remains is to prove the third property, closeness with respect to scalar multiplication. So that's part 3. Closeness with respect to scalar multiplication. Now we'll proceed in a pretty similar way. Again, we'll consider a solution x bar, and we'll also consider a scalar, we call that lambda, and then we will show that lambda times x bar satisfies all equations from this system of linear equations. So, consider a solution x bar in S and a scalar lambda in R. And again, let's define Z bar to be lambda times x bar. Then, for all I in M, so again, for each equation, we have the following. Well, if you look at ai1 Z1 bar plus ai2 Z2 bar and so on up to ain Zm bar, we want to show that this is 0 so that we can see that Z solves this equation and is therefore contained in the set S. We do this again by just substituting what we know about Z bar. Z bar is lambda times x bar. So we have lambda times x1 bar plus and so on up to lambda times xn bar. And again, we can factor out the lambda here and collect all the x terms. So we have ai1 x1 bar and so on up to ain xn bar. And once again, this part here, we know that this is 0 because x bar is a solution to the system of linear equations. So this is 0 because x bar is contained in S. And that means what we have here is lambda times 0, which is, of course, equal to 0. So, Z bar solves the equation, and that means, as this is true for all equations, Z bar is contained in the set S. So that concludes the proof, and as a sign of conclusion of that proof, successful conclusion of the proof, we make this little square sign here. You can also write QED if you want to. So that's the characterization theorem for homogeneous systems of linear equations. The solution space of a homogeneous system of linear equations can only be a linear subspace. Just as a quick example, what does that mean for R to the 2? So for an SLE, system of linear equations in R2, meaning we have two variables, we can have the following cases. Following can occur. And I should mention that we are only talking about homogeneous equations here. So right-hand side is 0. First case that could happen is we have a unique solution. And if that is the case, this unique solution needs to be 0, the alt 0 vector, because that is always a solution for the homogeneous case. So we could have a unique solution, 0, 0. Or we could have a linear subspace. And what are the linear subspaces of R2? We characterize those a little later. But basically, apart from this one point, which is also a linear subspace, there's only two possibilities that could occur. The other extreme is the solution space could be R2. So every point is a solution. And then there's one case in between. And that is linear subspaces that are smaller than R2, but larger than just one point. In R2, there's only one kind of subspace with that property, and that is any line through the origin. So those are the only solution spaces that can occur for two variables. The selection, of course, gets richer for more variables. We'll deal with that in more detail later on when we characterize vector spaces in a little more detail. Before we do that, let's have a quick look at the inhomogeneous case. That's going to be the next theorem. What about an inhomogeneous system of linear equations? Well, things are a little more complicated there, but the structure is not really that different. So let AB be an inhomogeneous system of linear equations in tableau form. And we'll assume that the solution space is not empty, because that is, of course, a possibility within homogeneous systems of linear equations, but the empty set does not have a lot of interesting structure, so we'll exclude that. So we'll assume that is non-empty solution space, and we're going to call that S. Now those do not have to be systems, those do not have to be linear subspaces, but they will be something very similar. What this theorem will tell us is there is a close relation between the solution spaces of inhomogeneous systems linear equations and their homogeneous counterpart. So if you just replace the right-hand side by zeros, that's the corresponding homogeneous system of linear equations. And the solution space for the inhomogeneous case is almost the same as for the corresponding homogeneous system of linear equations, but it might include a shift. So you have this linear subspace, and then you just shift it by some constant vector, up or down or left or right or whatever you want. And that gives you the solution space of the inhomogeneous system of linear equations, if you do the right shift, of course. And this theorem is in particular telling us what the right shift is. So let's write that down fully. So furthermore, we need this shift vector. Let S bar in S be some arbitrary solution to the SLE, and let U be the solution space of the corresponding homogeneous system of linear equations. And that will be the system A, and the right-hand side is just replaced by 0. And what this theorem tells us is then the solution space S has the form S bar plus U. That means each element in that space will look like S bar plus small u, where small u comes from this capital U. So basically we take the homogeneous solution space and we shift it by S bar, and S bar needs to be some arbitrary solution of the inhomogeneous case. So it would be sufficient to determine just one solution and then do the homogeneous case, and we can just shift that. We'll deal with spaces that look like this a little later in more detail once again, once we have a better understanding of vector spaces and their properties. Again, I'd like to give you a proof of that theorem to give you an example of how to deal with these situations and what that actually means to help you gain a better understanding. So, what this relation here says is basically two things. First, it says if you take an arbitrary solution from U, from the homogeneous case, and add that S, then the result is always a solution of the inhomogeneous case. That's the first outcome. The second one is if you take an arbitrary solution of the inhomogeneous case, then it always has this form. So there is always a U and an S bar, such that you can write your solution in that way. And we need to prove both parts of this equation, of course. Let's start with the easier case, where we start with the solution of the homogeneous system, and then see that S plus that, or S bar plus that solution solves the inhomogeneous system. So this is part one. First, let U in U, or U bar in U, be a solution to the homogeneous SLE. And again, we'll take an arbitrary I and look at the corresponding equation. Then for each I in M, again, we assume we have M equations. We have the following. Well, let's look at AI1. Let's look at the solution S bar plus U bar. We want to see that this is actually a solution of the inhomogeneous system of linear equations. So let's substitute that here. So we substitute S1 bar plus U1 bar for X1, and so on, up to AIN times SN bar plus UN bar. Similarly to what we've done before, we could now collect those two parts. We collect the S parts and we collect the U parts. And we get AIN S1 bar plus and so on. AIN SN bar. And for the U's, we have AI1 U1 bar plus and so on plus AIN UN bar. And what do we know about this? Well, we know that S bar is a solution to the inhomogeneous system. So this here is equal to BI because SN bar solves this inhomogeneous case, right? So this is BI. And that second part, this is 0 because U bar solves the homogeneous case. So what we have is BI plus 0, which is of course BI. And that means S bar plus U bar solves this equation. And as we did that for arbitrary I, arbitrary equation, it solves the inhomogeneous SLE. So for every solution of the homogeneous SLE, we get a corresponding solution of the inhomogeneous SLE. Okay, so we know there are at least as many solutions to the inhomogeneous SLE as for the homogeneous case. Now, the solution set is at least as rich. And now we need to exclude that there may be more solutions to the inhomogeneous case. So what I'm going to prove now is that every possible solution of the inhomogeneous system can actually be written in that same form. So there are no solutions that do not have that form. And to that end, we'll consider a second solution and then try to produce a suitable U. So now consider a second solution, T bar in S to the inhomogeneous system. AB. Then we'll define a vector U by simply taking this T bar and subtracting S bar. And of course we did that because that means, in other words, T bar is S bar plus U. So T bar has the desired form. The only question is U bar actually a solution to the homogeneous system? So is U contained in U? Meaning, is U a solution to the homogeneous SLE with the right-hand side 0? Well, let's see if we can prove that. And again, we'll just take an arbitrary I in M. So any equation. And we get AI I1, U1, plus, and so on, plus AIN, UN. And we'd like to see whether this is 0, because that means that U solves the homogeneous system of linear equations. Well, let's substitute what we know about U. We know that U is equal to T bar minus S bar, so U1 is T1 bar minus S1 bar, and so on, up to UN. UN is Tn bar minus Sn bar. And then again, let's collect the T parts and the S parts, and we get IN1 T1 bar plus, and so on, AIN Tn bar. And for the S parts, there's always a minus in front of the S parts, so we factor out the minus, and then we have AI1 S1 bar plus, and so on, AIN Sn bar. And now remember, both S bar and T bar are solutions to the inhomogeneous system of linear equations. And what that means is this evaluates to BI, and this here also evaluates to BI, because both T bar and S bar solve the system AB. So what we get is BI minus BI. Well, of course, what is that? BI minus BI, well, that's 0. And that means this expression here evaluates to 0. Or in other words, as this is true for all equations, U is a solution to the homogeneous SLE. Or in other words, more formally, U is contained in capital U. So every solution of the inhomogeneous system of linear equations can actually be written in that form. And that means if we produce just one solution, S bar, and have the solution space of the homogeneous system, of course, then we can immediately write down the solution space of the SLE. It basically has the same structure, the same properties, it's just shifted a little. And again, we'll deal with that a little later. So let me just write down that summary. What that means is basically the solution space of an inhomogeneous SLE is obtained by adding a particular solution, any solution of the inhomogeneous case, and that's called a particular solution, of the SLE to the solution space of the homogeneous SLE. Or in other words, the structure of this solution space is a translated linear subspace. So there's this shift, this translation by S bar, but otherwise the structure is totally the same. Okay, that concludes this first investigation of the structure of solution spaces of systems of linear equations. We're going to deal with properties of vector spaces in more detail in the upcoming videos. And then we'll revisit this characterization and see if we can add some more details to that. I'll see you then.